Well, hello everyone. Um, in this video, I'm going to explain, or I'm going to try to create a mini heap, and then I'm going to try to use this mini heap to print the data in a sorted way. Like, I'm not trying to sort the data inside the mini heap. No, I am just going to use the mini heap to print the elements inside the mini heap from the smallest value to the greatest value. So this is my project here. I'm going to go through the elements instead of me typing everything, which is going to make the code look a little bit long. What I'm going to do, basically, I'm going to go show you the code that I created. So here we go. At this point, I do have a class called miniheap that I created. In this miniheap class, I have a private section. I have a public section. In the private section, I created a vector. I call it container, and I have two integers. One of them to store the size of that container, which I can use the size variable if I want to. And then I have a variable called last, which basically is going to be holding the index of the last element inside that container vector. Okay, so here we go. Let's start with the first part, which is the public sections. Sorry, that's not the first part. I do have a default constructor where I'm going to set the least to be -1 and the size to be 0, of course, because the container is empty at the beginning, so I cannot put the index to be equal 0 because actually we do have an element with index 0, so we're going to go one step further to the left, which basically means -1. And the size is going to be 0 at the beginning. Now we do have mainly few functions. We have the add. This is how I add an element to the heap. I can remove an element from a heap, and I can return the size, check if it's empty or not, and get the root of that heap, which basically is going to return the first element inside that container. Now let's go ahead and talk about how do we add elements to that heap. Now, if you go to the main function here, I create the mini heap. I call it heapy. And then I start adding those elements to the heap. Now we know every time you insert an element inside the heap, it has to go to the right place. And then after that, you're going to have to figure out if it's the rules of mini heap is still kept there or not. And you're going to start doing the swapping. I'm not going to go through the methodology, assuming that you already know how does it work. I'm just here concerned with the code itself. So I'm adding those elements to this mini heap. Now, let's go ahead and have a look at how do we add elements. The idea here is very simple. What am I doing here? I'm having three variables here. One of them called a parent, child, and x. X is just a temporary variable that I'm going to need to store a certain value. Now, whenever you add an element to a heap, you basically have to increase the size by 1. And then after that, you have to increase the index last variable by 1. And then you're going to use... That's basically going to give you the index of the last element. And then after that, you're going to push back the data that you want inside that container, which again, I'm going to assume that it's just to add the element. Once the element is added, I need to find out if that element is in the right place or not, and it depends on the relationship between the parent and the child. So what I'm doing here, I'm trying to calculate what is the index of the parent and what is the index of the child. And before I do that, I have x here calculated. We know that the parent index equal the child index -1 divided by 2. So what am I doing here? This I minus 1, which basically is the last -1, I'm going to keep it inside a variable called x. I'm going to use that as an indicator that, because again, as I'm going to be moving up to the root, at a certain point, I need to make sure that I'm not going to get an index of -1, for example. There should be a point where I should start. And that's what I'm doing here. I'm trying to calculate this x, and I'm going to use that x as an indicator that I got to the top. I have to stop at that point. Again, the problem is I can use 0, but 0 is still acceptable because it's an index of the root. I'm talking about after that I have to stop there because there is nothing after that. So first thing first, I'm calculating x. From x, I'm calculating the parent, and I'm calculating the child. Now, I do have a while loop here. In this while loop, I just have these two conditions. First of all, if the parent was greater than the child, so that basically means it's not a mini heap anymore. And at the same time, x is actually greater or equals 0. So we're still in the right area. The moment x get -1, that's where you're going to have to stop, because you reach the root and there's no point of going on, because there's nothing to keep going on with it. So if I get this condition to be true, all I have to do is swap the parent with the child. And then after that, I have to update my values. So basically, what was parent is going to be the child now. So the child is going to hold the address of the parent. And then I'm going to have to calculate the new parent depending on the address of the new child. And then I'm going to go back here and try to compare the parent with the child. If it happens that the parent is actually greater than the child and x is still greater or equals 0, then you're going to keep going until you got the element in the right spot. So when you do this, you basically will be able to get the right elements in the right spots. And this is, again, my heap. And if I just run it, I've forgotten. I need to actually have a breakpoint here. I'm just going to let me just run it. Okay. Now if I go here to this heapy and I go to the container, you'll see that those are the values: 10, 20, 50, 40, 30, 90, 60, 100, 70, and 80. And now if you try to draw those elements in a tree graphically and you study the relationship between the parents and the child, you will get a mini heap. So I am done with the add function. Again, you're going to have to declare some variables, perform some calculations, add the element, and then after that, this is the most critical part, is where you're going to have a parent, child, and the x value. You'll have this while loop that will go until one of those two conditions became false. And you're going to keep swapping, updating the child and the parent indexes, swapping, updating the parent and the child indexes until x get to a value of -1. That basically means I got to the root, I processed the root, I am done. There's no need for me to continue because there's nothing to continue with. Or I got to a point where actually the parent was less than the child, so there's no need for swapping or anything. So this will be the end of the add function. Now, if I want to remove an element, which basically is going to be a little bit complicated, but it's okay. What do I do? Let me just go back to the main function. In the main function, what did I do here? I created a variable. I call it size, and then the size is going to equal the size of the heap. And then here I got a for loop. In my for loop, what am I doing here? I am going to show the root, and then I'm going to remove the root. And when you remove the root, you need to know that what's going to happen. We usually go and take the last element inside that heap and we replace it with the root. And then after that, we're going to have to ask ourselves if the value that you have there will keep and maintain this heap to be a mini heap, which basically it will not. So probably, again, mostly one of those left child or right child will be less than, if not both of them, will be less than that root. So you're going to have to do swapping, and then you're going to have to continue that way to maintain the fact that the root is always smaller than any child. So once you retrieve the root, you're going to have to remove it. And when it's going to be removed, it's going to be replaced by the next smallest value. So how is that going to be done? Well, let's go ahead to the remove function. In the remove function, as you can see here, first of all, I'm going to check for the size. If it doesn't equal 0, that basically means I have elements, I can remove them. And what am I doing here? I am updating the first element with the last one. I'm assigning the last value inside that array to that container. And then after that, I am reducing the size by 1 and reducing the last by 1. And then after that, I call this function here, which is the heap swap function. Now, if I get to a point where the size was equals 0, that basically means there's nothing to remove. That's why I'm typing nope here. So what's going to happen here? I am basically going to pass the container after I actually updated the first value, updated the size, and updated the last. I'm going to pass the size, and I'm going to pass I as the index of the root. And we do have this function. It's not part of the class. So if I go here all the way to the top, I call it heap swap, and I'm passing, and this is very important, you should pass a reference for that vector, because we know when you pass a vector to a function, you're passing it by copy, not by address. So it has to be referenced, so whatever modification is going to be applied here, it will be applied to the original container. Okay, so I got the container here, I got the size here, and I got the root index at that point, which basically at the beginning of this recursive process is going to be 0. So I'm going to calculate the smallest index. I'm trying to find which value is the smallest out of those two children, the left child and the right child. So I'm going to calculate the left child and the right child, store them in L and R. And here it is. I will say as long as L is less than N, and N here, remember here is the size of the data. And at the same time, the value in that vector for the left child is less than the right child, I'm going to update the smallest to be the left index. Now, I'm assuming that this is going to be the smallest value. Now, what do I need to do? I need to compare the smallest with the right child and see if the right child is smaller than the left child. So those two lines are basically for me to look for the smallest index, the index with the smallest value. And I'm talking about the relationship between the root, left child, and right child. The moment you find the smallest, you're going to come here to this if statement here, and you're going to say if smallest doesn't equal I. What does that mean? That basically means the left child or the right child actually has a smaller value than the root. If that's not the case, that basically means the root has the correct value. There's no need to do anything. So the moment you find a case like this, you're just going to have to swap that root with that smallest child, which could be the left or could be the right. The moment you're done with that part, you're going to have to do this again. Calling the same function again, recursively, passing the same size of data, and most importantly, this time, what was the previous root, which was 0, now is going to be the new one. If you go to the left, it's going to be the left child. If you go to the right, it's going to be the right child. And then, recursively, you're going to go back here and complete the process. Now, if I go back here and run it, you'll see that the data that I entered, and after I started removing those elements one by one, I got the data to be printed in a sorted way. Now, what I'm going to be doing here, I'm going to go through the code, show you that code piece by piece. So here it is. This is my function again. I call it heap swap, and the heap swap basically is just a function. It's not part of a class. I divide into 3 sections. The declarations for the variables left and right and smallest. This part is where I'm trying to find out which indexes has the smallest value. And then after that, I am going to check if I got the smallest to be left or right. Then I have to swap. And then after that, I'm going to recursively call the function again until I'm done. This is the part where I have the mini heap. Again, this is the private section. This is the public section. In the public section, we got the constructor, default one. And then after that, we have the add function in this area. And the add function, as you can see here, just like I said before, I declare 3 variables. After that, I had increased the size by 1, last by 1. I'm adding a new element here. And then after that, I add the element by using the pushback function of the container. Right after that, I'm going to start calculating the parent, the child, and the x value. This is my while loop. I'm always going to compare the parent with the child I'm trying to add here. So if it happened that the parent was less than the child, if the parent was greater than the child, then I'm going to have to do a swapping. And once you can perform the swap, you have to update the child and the parent, of course, again and again. And most importantly, I have this condition here that I added just to make sure once you get to the root, you're going to use the root for one time, and then after that, you're done. And that's basically how the add function will work. Now, after that, we got the move function plus those get size empty and get root. Remove function here, which basically will have an if statement to check if there's an element to remove to start with. If we have elements, then remove them. Otherwise, show a message here. Now, what are we going to do? We're going to assign the last element inside that container to the first element. That's how we do it. And then you're going to reduce the size by 1, reduce the last by 1. And then we're going to call this heap swap function by passing the container size and the root ID index, which is 0 in this case. And I talked about the heap swap at this point. In the main function here, this is me testing everything, and that's basically how you answer this question, or this is how you perform a heap sort algorithm. So this will be the end of this video. I'll see you guys later.